Category O, Lecture 26, Primitive Ideals. If R is a ring, then an ideal I of R is called primitive if it is the annihilator of some simple R module. We denote by prim of R the set of all primitive ideals of R. Let us note that prim R is a topological space with respect to the so-called Jacobson topology. The closure of a given set of ideals is the set of all ideals which contain the intersection of all elements, that is, ideals, in the original set. So let us denote by Ir of R the set of all simple R modules, and by Ir F of R the set of all faithful simple R modules. Then the set Ir of R decomposes as the disjoint union of the sets Ir F of R modulo I, where I is a primitive ideal of R. So this shows the relevance of the description of primitive ideals for the study of R modules. Description of primitive ideals is a natural first step towards the general classification of simple R modules. The later problem is usually very difficult. Now let us recall Duflo's theorem, which we already mentioned in the course some time ago. Let G be a semi-simple finite-dimensional complex Lie algebra with a fixed triangular decomposition into a direct sum of the negative part n minus, the Cartan subalgebra H, and the positive part n plus. Let lambda be a weight, that is an element in the dual space of the Cartan. With each such lambda, we can associate the corresponding Verma module delta of lambda and its simple quotient L of lambda. Let U of G be the universal enveloping algebra of G. The theorem of Duflo asserts that every primitive ideal of the universal enveloping algebra is the annihilator of some simple highest weight module L lambda. For full proof of this theorem, we refer to original paper of Duflo from 1977. Let us now discuss the minimal primitive ideals. Recall that every simple U of G module has central character. Let Z of G be the center of U of G. We also know that the annihilator of each Verma module delta lambda is generated by its intersection with the center. This means that it has a form U of G times M lambda, where M lambda is a maximal ideal in Z of G. We also know that M lambda is equal to N mu if and only if lambda belongs to the orbit of mu under the dot action of the Weyl group W. And we also know that every maximal ideal in the center is of the form M lambda for some lambda. Also recall that if lambda is antidominant with respect to its integral Weyl group, then delta of lambda is equal to L of lambda. From this, it follows that the ideals U of G times M lambda are exactly the minimal primitive ideals of U of G. So they are the annihilators of antidominant Verma or simple highest weight modules. And the aim of this lecture is to classify the primitive ideals which contain the minimal primitive ideal UGM0. So M0 is the central character of the principal block of category O. So we would like to classify these primitive ideals and describe inclusions between them. The answer is given by the Barbasch-Vogan theorem. So let O0 be the principal block of O. So W is a Weyl group, rho is the half of the sum of all positive roots, and we have the dot action W dot lambda is equal to W of lambda minus rho plus rho. So this is the dot action of W. So the simple objects in O lambda are LW, which is the notation for the simple highest weight module with the highest weight W dot lambda, where lambda is equal to 0. And we denote by less than or equal to sub L the Kazhdan-Lusztig left order on W. The theorem of Barbasch and Vogan asserts that for two elements x and y in W, the annihilator of Lx is a subset of the annihilator of Ly if and only if y is less than or equal to x with respect to the left order. And there are two references. The first paper from '82 is for the classical Lie algebras, and the other paper from '83 is for the exceptional Lie algebras. So here is an SL3 example. So in the SL3 case, the group W consists of im, s, t, st, ts, and w0. Here is the order on the left cells in this group. So we have four left cells. E is the minimal left cell, and W0 is the maximum left cell. There are two non-singleton left cells, one of them consisting of S and TS, and another one consisting of T and ST. They are not comparable with respect to the left order. So from this description, Barbasch-Vogan's theorem asserts that the annihilator of LW0 is the minimum primitive ideal for this block. The annihilator of Ls is equal to the annihilator of LTS because S and TS form a left cell. The annihilator of LT is equal to the annihilator of LST because T and ST form a left cell. And the annihilator of LE is a one-dimensional module, so this is UG times G. This is a maximum primitive ideal for this block. And this ideal has finite codimension. In fact, this ideal has codimension 1. Let us now discuss how right cells and right order can be defined in terms of the mu function. Recall that we have the so-called Kazhdan-Lusztig mu function, and this is a function which associates to a pair of elements in W a non-negative integer. If W is an element in W and S is a simple reflection such that Ws is less than or equal to W, then the multiplication of the Kazhdan-Lusztig basis element HW underlined and HS underlined is equal to HW underlined with the coefficient V plus V inverse. And in the other situation, where Ws is greater than W, then the product HW underlined and HS underlined is equal to HWS underlined plus the sum over all x which are smaller than W and such that xs is smaller than x of hx underlined with the coefficient mu xw. The usual convention is that mu WWS is equal to 1. And since the Hecke algebra H is generated by the Kazhdan-Lusztig elements for simple reflections, we obtain that the right preorder on W is generated by the mu function in the sense that it coincides with the minimal preorder on W, which contains all pairs WWS for W in W and S in S with WS greater than W, and also all pairs W, X, for which X is smaller than W, and there is a simple reflection S such that Ws is greater than W, Xs is smaller than X, and the value of the mu function at the pair xw is non-zero. Similarly, we can give a description of the left cells and the left order using the mu function. Again, if W and S are such that SW is smaller than W, then the Kazhdan-Lusztig element for S times the Kazhdan-Lusztig element for W gives us the Kazhdan-Lusztig element for W with the coefficient V plus V inverse. In the other situation, when SW is greater than W, then the product of HS underlined times HW underlined is HSW underlined plus a similar sum as before. The only difference is that now Sx should be smaller than X. And again, we have hx underlined with the coefficient given by the mu function. And the same convention for the mu function, that the mu function between W and SW is 1. And the same assertion that the left preorder is generated by the mu function in a similar sense as before. So it's a minimal preorder on W which contains all pairs W, SW for the situation as W greater than W, and also all pairs W and X such that X is smaller than W, and there is a simple reflection such that the corresponding mu function between X and W appearing in this sum is non-zero. So using this, we can actually show that the annihilators of simple highest weight modules are constant on left cells. So let W be in W and S a simple reflection such that SW is smaller than W. Then we can consider Joseph's completion functor associated to the simple reflection, and because of our assumption that SW is smaller than W, Js of LW will be non-zero. And since W in this situation is S infinite, we also get that Js of LW will be equal to the value of the Enright's completion functor Es on LW. And recall that Enright's completion functor is defined using first localization and then taking the locally finite part of the module. From this definition, it follows directly that for any module n, its annihilator is naturally a subset of the annihilator of the Enright's completion of n. In other words, the annihilator of LW is a subset of the annihilator of GS LW. We know that GS LW has simple socle LW, and the quotient of it by the socle has the form which reminds us the formula from the previous slide. So we have LSW and then plus the direct sum of LX's, where x is greater than w and sx is greater than x, with the multiplicity given by the mu function. So comparing this with the formula of the previous slide, it follows that if x is left less than or equal to w, then the annihilator of LW is a subset of the annihilator of LX. In particular, if X and W are in the same left cell, then they must have the same annihilator. So this proves the first half of Barbasch-Vogan's theorem. So let us do an SL3 example. So in the SL3 example, we have W is E, S, T, ST, TS, and W0. And here is a picture of the Brugha order, which is adjusted a little bit to reflect the weight picture inside the dominant Fermat module. So the mu function corresponds to the number of edges in this picture between different points. And so we can easily compute that if we write complete W0, we just additionally get TS. So the S completion of LW0 modulo the original LW0 gives us LTS. So the annihilator of LW0 is included into the annihilator of LTS. When we T and write complete LTS and factor out the original module, we will get LS. So if you start from here and go by S, we get LS because there is no mu function between these two elements. There is no H here. And so the annihilator of LTS is a subset of the annihilator of LS. Next, when we S and write complete LS and factor out LS, so we now go in the direction of S, we will get LE, but also LTS. So this element is S finite, and we have a non-zero mu function between them. So this implies that the annihilator of LS is a subset of the annihilator of LE, and the annihilator of LS is a subset of the annihilator of LTS. So we have two inclusions, and consequently the annihilators of LS and LTS coincide. And we know that S and TS form a left cell in this picture. Similarly, one shows that the annihilators of LST and LT coincide, and here ST and T is another left cell, which is not a singleton left cell. in this picture. How can we now continue to completely prove Barbasch-Vogan's theorem? So recall that each right cell R contains a unique Duflo element denoted dr. So this element is in fact an involution. Therefore, each left cell L also contains a unique Duflo element, namely dl, which is by definition d of L inverse. L inverse is now a right cell, and this is an element in the corresponding right cell. Let us denote by IL the annihilator of LDL. So we know that annihilators are constant on left cells. So in each left cell, we pick the Duflo element, and now our aim is to compare the annihilators of these Duflo elements. So we need to compare these different ILs. Note that if we take IL, it contains the minimal primitive ideal UG times M0. And if we factor it out, the outcome is a GG sub-bimodule of UG modulo this minimal primitive ideal. So this is just by the minimality of M0. And this quotient UG modulo the minimal primitive ideal is the dominant projective object in the category H0011 of Harish-Chandra bimodules. So in particular, the quotient of IL modulo the minimal primitive ideal is an object in this category. So we need to compare all these different objects of this category of Harish-Chandra bimodules. And by the Bernstein-Gelfand equivalence, these are certain subquotients of the dominant Verma module in category O. So in what follows, we will try to compare these subquotients. So let us define the module delta R. So we fix a left cell L, and we denote by R its inverse, so it's a right cell. So denote by delta R the unique quotient of delta E, whose socle is LDR shifted by minus the value of the A function of R. So this is uniquely defined because delta E contains a unique subquotient of this form. So this was the definition of the Duflo element. So by definition, we have a short exact sequence, delta E surjects onto delta R, and we denote by KR the corresponding kernel. Recall that for two G modules M and N, we denote by L from M to N the set of all adjointly locally finite elements of the GG bimodule of all linear maps from M to N. Also recall that for any G module M, the quotient of U of G by the annihilator of M is a sub-bimodule of L MM. Costant's theorem asserts that L of delta E is equal to the quotient of U of G modulo the annihilator of delta E. So in other words, Costant's problem has a positive solution for delta E. So we claim that U of G surjects onto L of delta R, or in other words, that L of delta R is U of G modulo the annihilator in U of G of delta R. So proof of the proposition. So we apply the left exact bifunctor L blank blank in each argument to the short exact sequence given by the definition of delta R. So if we do this, we get the following commutative diagram with exact rows and columns. And in this diagram, we observe that this magenta map from L delta E to L delta E delta R is surjective. So the functor L delta E blank is left exact by definition, but since delta E is projective in O, this functor is exact. So this map is surjective. And L delta R naturally embeds into L delta E delta R, which implies that L delta E, which is U of G modulo the annihilator of delta E, surjects onto L delta R, which was exactly the claim of the proposition. So now we want to compare L delta R with L of the simple module L dr LDR. The claim is that L of delta R, so U of G modulo the annihilator of delta R, is a subbimodule of L, LDR, LDR. Proof. So we apply the left exact bifunctor L blank blank to the short exact sequence. LDR is by definition the socle of delta R, and we denote by CR the cokernel. So if we apply this bifunctor to the short exact sequence in each argument, we get the following commutative diagram with exact rows and columns. Now we only have inclusions from the first row to the second row and from the first column to the second column. Lemma, this element L from LDR to CR and this element L from CR to delta R are 0. So if we accept this lemma, then 0 here gives us that LLDR is isomorphic to LLDR delta R. And the 0 here implies that the map from L delta R to here is injective. So this gives us exactly the assertion of our proposition. So to complete the proof, we now need to prove this lemma. Okay, proof of the lemma. Recall that delta R belongs to the Serre subcategory OR hat of O0. So this is a Serre subcategory generated by all simples whose indices are right less than or smaller to the right cell of R. And hence any simple subquotient LW of delta R has this property that W is right less than or equal to dr. Well, from the definition of Duflo element, we also get that all other simple subquotients of delta R, apart from the socle, are actually given by simple modules whose indices are strictly smaller with respect to the right order than dr. But when we apply projective functors, we cannot increase the elements with respect to the right order. This means that for any projective functor theta, if we consider theta CR, then any simple subquotient of this module has the index which is right strictly smaller than our right cell R. In other words, we cannot have any home from LDR to theta CR, and we cannot have any home from theta CR to delta R, because delta R has simple socle LDR. But this means that the multiplicity of any simple finite dimensional module V in L, LDR-CR, and in L, CR delta R should be 0, because it is given as a sum of such home spaces. In other words, L, LDR-CR is a 0 bimodule, and L, CR delta R is a 0 bimodule, which proves our lemma. So now we can prove Barbasch-Vogan's theorem. We need to prove that, given two left cells and an L prime, the annihilator of L dl prime is a subset of the annihilator of L dl if and only if L is less than or equal to L prime with respect to the left order. From the previous slides, we already seen that the annihilator of LDR is the annihilator of our module delta R. And the image of delta R in H0011 is by definition stable under Sergel side swapping self-equivalence. So in particular, it follows that any simple subquotients of delta R has the property that its index is less than or equal to dr with respect to the left order. And this then reduces the problem of inclusion of annihilators to the problem of projections of different modules delta R. So in other words, the module delta R, or we can denote it also by delta L, is the image of UG modulo the annihilator of L dl under the Bernstein-Gelfand equivalence. So therefore, if L and L primes are related by the left order, then delta L prime, of course, surjects onto delta L. If they're not related in the left order, then delta L contains LDL, which is not a subquotient of delta L prime by the above properties, and therefore delta L prime cannot surject onto delta L. And this completes the proof of Barbasch-Vogan theorem. So in the second part of this lecture, we will comment on the description of left, right, and two-sided cells in type A. Let us first recall Robinson-Schensted correspondence. Consider the symmetric group Sn and let lambda be a partition of n. Then we can consider the set SYT lambda of all standard Young tableaus of shape lambda. Then the Robinson-Schensted correspondence asserts that there is a bijection between Sn and the disjoint union over all lambda, which are partitions of n, of the sets SYT lambda times SYT lambda. So there is a bijection between permutations and pairs of standard Young tableaus of the same shape. So let us fix such a bijection, which is given by Schensted insertion algorithm. So we will need the notation that the Robinson-Schensted correspondent of W is a pair PW-QW, where PW is the insertion tableau and QW is the recording tableau, and lambda is the common shape of PW and QW. This algorithm is originally described by Schensted in his paper in 1961, and for more details, one can read Sagan's book, The Symmetric Group, from 2001. Now we can describe cells in type A. Theorem due to Kazhdan and Lustig. For x and y in Sn, we have x and y are right equivalent if and only if px is equal to py. X and y are left equivalent if and only if qx is equal to qy. And x and y are two-sided equivalent if and only if the shape of px is equal to the shape of py. So for example, for S3, which consists of the elements E, S, T, ST, TS, and W0, we have that the shape of PE is 3, the shape of PW0 is 1, 1, 1, and the shape of insertion tableaus of all other elements is 2, 1. So the insertion tableau for S and ST is 1, 3, 2, and for T and TS is 1, 2, 3. The recording tableau for S and TS is 1, 3, 2, and the recording tableau for T and ST is 1, 2, 3. So S and ST, this is a right cell, T and TS, this is a right cell, S and TS is a left cell, and T and ST is a left cell. This is an example how you can apply this theorem. So in order to discuss the proof, we need to first talk a little bit about cell modules. So let L be a left cell in W. Denote by L hat the set of all elements in W which are left greater than or equal to L. And let L hat prime be the set of all elements W in W which are left strictly greater than L. Consider, inside the Hecke algebra, the span of all Kazhdan-Lustig elements indexed by W in L hat. So this should be a span over the Laurent polynomial algebra in V, because the Hecke algebra is an algebra over this ring. And similarly, consider the linear span N generated by Kazhdan-Lustig elements indexed by L hat prime. Then directly from the definition of the left order, we see that both M and N are left submodules of the left regular H module, and N is by definition a submodule of M. So the corresponding quotient M modulo N is called the Kazhdan-Lustig cell module associated to L and is denoted by CL. It is very easy to see from the definition that CL is free over the Laurent polynomial algebra, and the basis is given by the Kazhdan-Lustig elements indexed by W in our left cell L. And the specialization of V1 produces cell modules for the integral group algebra of W. And the important thing is that each cell module is, by construction, non-zero. We can similarly define two-sided cell modules for two-sided cells and actually refine this to a filtration of the left regular representation of the Hecke algebra by two-sided ideals. Given a two-sided cell J in W, define Ij as the linear span of all Kazhdan-Lusztig elements which are two-sided greater than or equal to our cell J. Consider the poset of all two-sided cells in W with respect to the two-sided order. So then, this collection of IJs is a filtration of H by ideals, and this filtration is indexed by the poset J. So if we specialize and extend the coefficients to the complex numbers, then we will get a filtration by ideals, and so each subquotient of this filtration is a sum of some isotypic components for this algebra. So now, from Kazhdan-Lusztig description of cells in type A, we have that if W is a symmetric group, then each cell module is simple over the complex numbers, and each subquotient of the two-sided filtration coincides with exactly one isotypic component of the left regular module. So in particular, it follows that for the symmetric group, two left cell modules are isomorphic if and only if the corresponding left cells belong to the same two-sided cell. So now we can sketch the proof of Kazhdan-Lusztig description of cells in type A. The key property of type A is that for any partition lambda, there is a parabolic subgroup W prime of Sn such that the corresponding longest element W0 prime satisfies that the shape of the insertion tableau for this element is equal to lambda. To construct such W prime, we should take lambda, transpose it, and then take the parabolic subgroup given by blocks of neighboring simple roots, which are written according to parts of the transpose of lambda. Okay, so if we keep this in mind, now consider some parabolic subgroup W prime of W and the corresponding longest element W0 prime. Recall that theta W0 prime applied to LW is non-zero if and only if W0 prime is left less than or equivalent to W. So this is from the previous lecture. And in general, we know that translations through W prime wall is non-zero if and only if W is the longest representative in W modulo W prime. Using the dominance lemma for partitions, one shows that under these assumptions, the shape of PW0 prime must dominate the shape of PW. So consequently, it follows that our poset J contains as a subposet some poset which can be refined to the poset of all partitions with respect to the dominance order. However, if we now add up all isotypic components for the elements of this poset, we will exhaust the left regular representation of the group algebra of the symmetric group. So J must actually coincide with this subposet. This means that J can be itself refined to the poset of all partitions with respect to the dominance order. Then we have seen that the parabolic category O categorifies the induced sign module. So using this, by induction on the dominance order, one shows that the cell module for the left cell of W0 prime is the simple CSN module which is given by the transpose of the shape of W0 prime. The transpose of the shape comes from the fact that this is the induced sign module and not just the usual permutation module. It's not the induced trivial module. Well, and then again, using the induction on the dominance order, you have to also to play against each other the left and the right order. You can complete the proof of the description of cells in type A. So in this proof we actually established that the poset J can be refined to the poset of partitions with respect to the dominance order. So in fact, there is a theorem proved by Geck that for the symmetric group and under our identification of two-sided cells with partitions of n, the two-sided order corresponds precisely to the dominance order on partitions. So the two-sided order for Sn is known. Again, from our description of left cells or right cells, it is clear that there is a natural bijection between left cells in Sn and the disjoint union of the sets of all standard Young tableaus for all partitions of n. It is still an open problem to give a combinatorial characterization of the left or the right Kazhdan-Lusztig order as the partial order on this set, even in type A. So the theorem of Geck is from his paper from 2012, so it's a fairly recent theorem. Let us now finish with some questions for PhD students. Question number 1. Prove that the quotient of U of G modulo the minimal primitive ideal corresponding to the element minus rho is a simple algebra. Question number 2. Check by direct computation using Enright's functors that in type B2 the annihilator of Ls coincides with the annihilator of LTS, and this coincides with the annihilator of LSTS. Question 3. Provide all details for the definition of the module delta R. Question 4. Compute all left cell modules in type B2 and show that they all are not isomorphic. Question 5. Find, for some Sn, an example of two different two-sided cells having the same A value. Thank you very much and see you next time.